Muito boa tarde. Obrigado pela presença. Eu sou o Tenente Coronel Haberman, vou ser o mediador dessa sessão técnica com a duração máxima de 50 minutos. Nesse ínterim teremos 3 apresentações. Deixa eu pegar minha cola aqui. A primeira delas, o título é em inglês, mas eu creio que seja em português, é isso? Apresentação. Vai falar em inglês, tá. O título é Pre-Correlation GNSS Spoofing Mitigation. A segunda, estudo de métodos de calibração radiométrica de sensores ópticos orbitais. E a terceira, detecção de drone com auxílio de rede neural convolucional. Uma das marcas do nosso simpósio é a pontualidade, né? Quero dizer o seguinte, que daqui 50 minutos a outra sessão vai ter que começar. Então eu vou adotar o seguinte critério, cada um vai falar 15 minutos, tá bom? Então totalizaremos 45 minutos e o tempo que sobrar ao final podemos fazer perguntas aí para os 3 apresentadores, tá bom? Então convido o primeiro palestrante, obrigado.
Obrigado. Boa tarde. Infelizmente meu aluno, Capitão Tenente Antônio, ele não pode participar. And that's why you have to listen to me today. My name is Felix. I'm a professor at ITA, and I will talk in English because I'm a foreigner and still learning the language. And as I have only 15 minutes, it's easier for me. So I will present a part of the master thesis of Antonio. It's about pre-correlation GNSS spoofing mitigation. I will just shortly introduce what is spoofing. Spoofing is that you receive the satellite signal from a global navigation satellite system. So, for example, GPS, in a system that will just relay the signal, and then the user will receive both the direct signal and the copy from the relay. This is the simplest form of spoofing. There's much more advanced things. So you can also use a signal generator to generate signals. But then you need a lot of information also from the user to successfully spoof him. And we will look into what can we detect to detect this spoofing and mitigate it. There's a lot of applications that need this. Definitely in the military area, this is one of the threats besides jamming. But jamming is easy to detect. I mean, your receiver will stop working, will stop telling you the position. In case of spoofing, it's more difficult to detect this because the receiver will continue working, but will give you a false position, and you will have to, detect whether this is the fact. And then even in the civil sector, this started to become an issue. In the US, they started to discuss about implementing this in aircraft because they have a lot of issues with spoofing. This is a simple thing that many people can just do. There's more and more private people who do this just for fun. There's people who do this for monetary reasons. For example, fishing authorities, they use GNSS for controlling where the fisherman is fishing. And if the fisherman wants to fish somewhere else and tell the authorities that he has a totally different position, he uses such devices. There's a lot of other of these applications also in the civil domain popping up. The Federal Aviation Association in the United States is very concerned about this, and they started several activities. And then my student found also this year, there's a $1.5 billion equipment development going on recently also in the US. I mean, this is the update of the current military equipment, and they're also looking into a lot of this stuff. The thing is also an issue in Europe with the Galileo system. So we tried to develop a system that is, and I hope this is the correct word, Sega, so blind. So it doesn't need any information from the user and doesn't need any information about the signal. So This is also applicable for cryptographic signals, so for the military service of GNSS. And what we will show you is how to detect, a simple method, how to detect spoofing with what we developed and how to mitigate this. So the idea is we follow the implementation of a standard military GPS receiver. So usually you have in military receivers, you have the receivers tamper-proof, you cannot open this. It's difficult to further develop technology inside of this receiver. So what they started is they built boxes in front of it. So they built a box. This is similar to the jamming, to these antennas that mitigate jamming in GPS. So they have an antenna, group of antennas. They do down conversion, digitalization. Then they have a box that is processing the signals, so removing the jamming. And then they do analog to digital, digital to analog conversion, up conversion again to the carrier frequency, and then they feed a clean signal to the receiver. So you can connect any kind of receiver without changing anything in the device, and you develop a new device in front of the receiver that is cleaning up the signal. Okay, and we're trying to follow this approach. We will now try to introduce also, besides the jamming that already exists, spoofing mitigation in a box. This is the scenario that we will consider for our simulations. It's just an example of a GPS constellation. We have here 13 satellites available. Usually you see less satellites in your receiver because they block out satellites below 5, 10, or 15 degrees. This is, as you can choose this as a user. And then we have our spoofer, which is a meaconing attack, so this replay attack. So then the signals are coming all from the same direction, right? So you have the relay transmitting all the signals from the same direction, while the satellite signals are coming from different directions. We have here azimuth, and we have here elevation. Here's elevation, while 0 is the horizon, and 90 degrees planet, and the receiver is positioned in the center. Yeah, we can formulate the signal. So we have like a superposition. This is the signal of one receive antenna, because we will consider here a multi-antenna system. This is just an example of a 7-element antenna array that we will consider. So we have a center element and 6 elements in a circle. This is approximately 20 centimeters in diameter here, or 10 centimeter radius. And we have here the directional information. The phase shifts between the antennas can be given by this A here. We have power of the received signals, and we have these, as GPS works with direct sequence code division multiple axis, we have here the sampled sequence delayed by a delay. Then we have also the Doppler information. We have this for I satellites, and then for the Q spoofers, for the Q spoofers, everything comes from the same direction. This is just how we can model the phase between the antennas with these polar coordinates. So this is then the signal of one antenna. Then we can put this together using the signals from all the antennas. And what we're now doing is we are correlating the signal from the center antenna, which we called antenna 1, with all the signals from the other antennas in the circle. So we use the center antenna as a reference signal and then correlate this with these signals in the ring. And then we can build here a vector from these correlations. This is a scalar. This is Hermitian, so transpose conjugate of a vector. And then we can put this all in a matrix. We can use a very simple direction finding method now using this data. Which is called the conventional beamformer. There's other methods, but this is a robust method and very simple to implement. And we end up with this. So what we are trying to do is we're trying to find power in space dependent on the two angles. So azimuth and elevation angle. And this is the expectation. So we're trying to find the power. We can see that the directions, if they are constant, the only thing that is statistical is inside this now, and then we can see that this turns out to be the spatial covariance matrix, which we can estimate by taking our measurements, so our signal, received signal, with this matrix, and then the Hermitian, and divide by the number of snapshots that we, from the correlation. Then we get an estimate of the spatial covariance matrix, and then we just have to evaluate this function. So this happens inside this box, just to remind you. And then the function for our scenario that we get looks like this. So here we have azimuth, here we have elevation. This is the normalized cost function. So we normalize this to 1, and we can see, this is great. We can see that the peak here is exactly in the direction. So we had 120 degrees azimuth for the spoofer, and we had a 25 degrees elevation. So approximately that. Here's a red dot. I don't know what happened. We use the PDF or the PDF have been better. Okay. Oh, yeah, I'm missing now everything. Why is the cost function so clear? Why does it show such? The receiver, the signals that we want him to track and to use for the positioning, they have to be a little bit stronger, than the satellite signals. So everything is a little bit stronger, and all our signals, all the satellite signals, they're coming from the same direction, because the relay is positioned at a certain distance and is transmitting all the received satellite signals towards the receiver. That's why That's why the power is accumulating in this direction. And that's why it's easy for us to detect this. And we can see very clearly, now we can see this. So 25, 30, so it's here, our maximum. So we can more or less detect the direction of the spoofer. This is very good. Now we have the dot here. So this is where we had 25 and 120. But you can see this is not easy. It's a 3, you have to search in 2 dimensions. So there's some complexity involved. It's how much the spoofer power is above the signal power. So it goes from 0 to 6 dB. And then we also increase the snapshots for our direction of arrival estimation. So with the conventional beamformer, we can see that the root mean square error for the azimuth, we get reasonable values in this area here. So above maybe 3 dB SSR, and using maybe 300, more than 300 snapshots. So we are below than 1 degree in root mean square error. And we can look at the same thing for the elevation. We can see the same area is interesting here. So if the signal, the spoofer to signal ratio is more than 3 dB, and we can, then we have to, with 300 or 400 snapshots, we can detect it. The correlation is important that we apply this, because usually GPS signals are 20 dB below the noise. So if you apply an oscilloscope to the band, you see just noise, so the measurement noise. And they only appear because of the direct sequence CDMA. If you know the signal and you know the structure, you can correlate with this known structure, this known sequence, and then the signal is above the noise after this correlation. We use this now with the reference antenna. We don't need to know anything about the signal, so it doesn't matter what kind of signal is transmitted. And then we can, in the next step, use this direction information, so we can then build a beamformer, right? So these are the signals from the different antennas transposed, and we can apply here a beamforming vector, and this would be then the output of the beamformer. What we can do with this information about the spoofer, which would be here the azimuth angle and elevation angle, we can null it, right? And the other thing is, what we want to do is we're trying to set up an optimization problem now for this beamformer. We want to maximize the power at the beamformer output. This is what this says, in a certain area. And what we can do is we can, for example, there's a lower limit of azimuth, higher limit of azimuth, lower limit of elevation, higher upper limit. And we can define. And what we did is like say, okay, above 20 degrees up to 90, we want to have the power as possible for all the satellites. The problem is we have only 7 antennas and we have 13 satellites, so we have usually not enough degrees of freedom to maximize the power to all the satellites, so we get some kind of best possible solution here. So this is the thing, and then we also we turn up the power of this guy. This will also maximize this function. The nice thing about this problem, this is an eigenvalue problem with a linear constraint, and we can just calculate the eigenvalue decomposition of this here. And we have here a projection matrix of the constraint. And we can calculate the eigenvalue decomposition of this. So we arrive at V lambda V Hermitian. In lambda, we have in the diagonal the eigenvalues, and these are the eigenvectors in the columns of V. And we choose the eigenvector with respect to the largest eigenvalue, and this is the solution of this problem. We have then we have to multiply this with G in order to because this is transforming our problem into the spoofing free subspace. And then we take the strongest eigenvalue in the subspace, and we have to transform it back in order to apply it here as a beamform. This is a good solution because there's no search, nothing. We just need an eigenvalue decomposition. And then in order to, and I will show you in the results, you will see why this is important. We can also, this null here is very distinct, and this is what happens if our direction estimate is not really good. What happens if we are moving? What happens if the transmitter, so the relay, the spoofer is moving? So if we want to accommodate this a little bit, and we see this has also other benefits on the further slides, we can broaden the null. And this is a matrix T where the I and J's element of this matrix is defined by this sinc function. Alpha is a design parameter. You can the more you increase alpha up to 1, you increase it above 1, it doesn't change much anymore. The null gets broader and broader. We introduce, and then we can just multiply this here with this matrix T. This is a Hadamard-Schur product, so it's an element-wise multiplication of the problem that we had here. Just multiply this element-wise with this matrix. Take the eigen decomposition, and we take again the eigenvector with respect to the strongest eigenvalue, and we arrive at our beamform. So let's have a look what we can achieve with this thing. So first I will show the results only for this solution and then for this. So this is for the first one. We see here the null of the beam of the spoofer. So the spoofer is very high. It has a very high, we can suppress it really good. And these triangles here are the satellites. So you see that some of them are amplified nicely. This is the array gain. So this goes up to 6 dB of gain in dark red here. And some of them are not really well amplified. So we might not we cannot process them anymore. So this is from the above. And if we now apply this matrix T, we see that the null broadens. And it's more homogeneous here. So this is from above. So we see the null is broader and less satellites are attenuated. I think this helps a lot, this matrix T, also to amplify the other signals. We perfectly can mitigate this. So yeah, this is my talk on behalf of New Pedro. So I showed you a very first step towards a blind spoofing mitigation method with this box that we can introduce before the receiver. We don't need anything to know, any knowledge about the signal, any knowledge about the system. We just need the band in which the box needs to operate. The only problem that we encounter is that we cannot receive these satellites, these three, because they're attenuated also with. Yeah, that's my talk. Thank you very much.
Thank you, Professor. Thank you very much.